Hello guys, Sir DB again here to continue my discussion on ACI, direct design improvement. So in my last video, I actually finished the important and significant aspect of the procedure and how to deal with the direct design method. But I also showed you what are the similarities of such method and differences of the direct design method with that of the equivalent method. So today, I will be focusing more on the equivalent frame method, which is of course also discussed in my previous lectures. But in this particular video, I want to emphasize some important points on determining what's the difference between the ACI and the direct design and the equivalent. So for the direct design method, remember that what we normally did is to first get the static moment MO, okay, on the basis of the formula WL2LN squared over 8, okay, and this is actually distributed longitudinally by means of table. So this MO will be distributed at the um, positive and negative regions of the frame, of the frame strip that we are talking about. So this frame strip is not different with the equivalent frame that we're talking about earlier. The only thing about this frame is it is discussed specifically, and it is discussed much detailed in the equivalent frame analysis. So this distribution is actually called the longitudinal distribution of moments. So we have the longitudinal distribution, which is done by simply using a table. No? So we have the table for this. No? So the table, which is simply an ACI coefficient table. So after doing this distribution, we move into the transverse distribution now of this. Okay, so the transverse distribution will now be done by simply recognizing the fact that we have to divide these static moment along the positive and negative regions of the frame into what you call the column strip and the middle strip. Okay, the column strip is defined in terms of one-fourth of the base span, which is L2. So we simply uh, get one-fourth of that on one adjacent side, and the other one-fourth on the other side, which will constitute your L2 over 4 boundary. Okay, so you have an L2 over 4 boundary. So in this L2 over 4 boundary, your middle strip will uh, constitute another L2 over 4 boundary on one side and L2 over 4 boundary on the other. So in total, so this MCS and MMS will simply be equal to L2 which is the boundary of your equivalent frame strip. Okay, so this is your frame strip. If you add this, okay, more so, your MCS will be divided into a B part, MB, and M slot. Okay, so where your MB is defined on the basis of the beam plus the projection. So the first thing I discussed on my first lecture, while the slab is the remaining part. Okay, okay. So this is now a distribution, transverse distribution of the moments coming from the static distribution on the regions, then dividing it into a column strip, middle strip, and the column strip into an MB and MS region. Okay, now for the ACI equivalent frame method, what differs is this. If this is the first step, we call this first step, we call this the second step, and the third step. What differs is on the second step. Okay, so the second step here, sorry, the first step rather, and the second step will now be different. The fact that in MO, okay, in your MO, we are simply making use of your static moments, okay, as the basis for your distribution, while here we are going to make an equivalent frame to analyze. No? So this equivalent frame is the same frame that we have done or we have created in the DDM. It's not different frame. It's just called an equivalent frame because at step number 2, we will make use of a structural analysis procedure of our choice, which is the advantage of the EFM because in this step we can use softwares to handle the computation. So a more exact distribution of your longitudinal distribution of your moments on the basis of the positive and negative regions along the frame strip can now be realized. The third is just the same. Okay, the same step involved. Of course, in the earlier days wherein the softwares are not yet that very popular, then we have to do it on the basis of moment distribution method. Okay, but now that softwares are there, we can actually mm, uh, get an advantage and make and produce accurate results. Now, on this step number 2, my discussion here will now be significant because these stiffnesses that we need in our frame analysis, our structural analysis, will now start on step number 2, will be involved in step number. And that is first considering the torsional rigidity or stiffness of the attached members. So basically, if we are talking of a frame analysis in three-dimensional, we now make use uh, of series of torsional beams, which are these beams here. So this torsional arms or torsional beams elements provides longitudinal stiffness on the basis of the analysis in this direction. So this is your long direction. Okay. So if I just want to make use of a particular frame analysis or conduct a frame analysis of one frame strip, I don't have to model uh, the whole structure, if, or especially if it's a typical bay frame, then this methodology or procedure is very fair. Okay, now for distortional beams, the stiffness formula is given by this, and take a look at the parameters. ECS is not new to us, C is not new, ISB is in the beam part, the moment of inertia of the slab beam part, IS is the remaining slab of the column strip. Now C2 is simply, if you are looking at this at this column in terms of this one, so C2 is the dimension uh, uh, on the transverse, along the transverse direction. So this is your C and this is your C1. So CT is the dimension along the transverse direction because this is a transverse torsional member. C2 must be there. L2 is the bay, no? This is now, if this is the transverse, L2 is the distance from this point up to the next frame column strip here. Okay. So so there's a column strip. So the distance between this up to this point is your L. Okay, and everything is just a matter of computation. Of course, the summation symbol here refers to the number of torsional beam elements. If this is one torsional beam, two, three, four, five, six, etc. So you just take the summation of all of these torsional arms, torsional elements that will add up to the stiffness of their long direction, thereby providing resistance to your lateral swaying. So this is a very efficient tool in dealing with a frame-by-frame analysis as far as the beam analysis um, is concerned, the equivalent frame method is concerned. Okay, so why do we need the KT then? The KT here will now be used in order to solve for the equivalent column stiffness. Because the equivalent column stiffness, KEC, is the one that truly represents the stiffness of each, okay, and every lateral frame resisting. Okay, so this is the lateral frame resisting system. Okay, so this is now the equivalent column which will be used, the stiffness of the column which will be used in our analysis. Okay, so for the flexural stiffness of the columns, these are the notes that you have to remember. That the height of the column is measured from the mid depth of the slab to the mid depth of the slab below, above and below. So if this is the floor, slab on top, and this is the floor, so you have to bear in mind that in the structural analysis, this must be at the mid depth. So this is the equivalent length of your column. So the moment of inertia is also taken as infinite from the top of the beam to the slab beam at the joint. Okay, so this is basically because the analysis at that time does not involve any software. Okay, so if you will try to look at the stiffness of a slab which is created on this entirety of the building diaphragm area, then we can say that the moment of inertia at the top and bottom of the slab is an infinite, has an infinite value. So I, okay, your I within this top and bottom of slabs will always be an infinite. How do you put an infinite value when using software? So you just create a big value, a value that is maybe 10 times greater than the other elements will represent an infinite value. Okay, because you cannot, of course, place the numerical value of infinite in terms of a real number. So you have to put some multiplier to make that uh, parameter produce calculations representing infinite values. So for the moment of inertia of flat slabs, wherein there are column capitals, okay, and drop panels, we have to see on the basis of, okay, if this is your slab and then this is the column, and you have a drop panel here, okay, so this is not, or maybe yes, a drop panel. The the uh, the column capital rather is this one. Of course, the at this point your moment of inertia is still infinite because the range of infinity is still within the boundary of the slab. So your 1 over I here will start from 0, and your 1 over I here will end equivalent to 1 over I of your column. Okay, so whatever is the column, because this is now at the level of this column stiffness here, whatever is the column's inertia here will represent a variable value of 1 over I from 0 to that of the value of the column. So this is 0 at the top to its value at the base. So this is the base. The cross section at the bottom of the capital. So if you want to input these values, again, IC can be computed on the basis of the formula for moment of inertia. And here 1 over I will simply be infinity. Okay, so I here will be 1 over 0, which is infinity. Therefore, infinity can actually be represented again by big numbers, maybe 10 times the moment of inertia for a simple column here. Then you can now provide a way on how to treat node to node. So if this is node here, you have node here, you have a node here, your moment of inertia, okay, for this particular point can actually be varied, no, from 1 over IC to 1 over I 0 to 1 over I infinity. Okay, so that is how to deal with flexural stiffness as far as columns with drop panels and column capitals are concerned. Okay, for the arrangement of live loads, when there is definitely no load pattern, the analysis should be made for it. So if you know that the load pattern for a certain, let's say, a restaurant is given by the arrangement of the tables and chairs, then if you are perhaps dealing with permanent seats in public assemblies, then no load pattern means that you have to place it in a fixed form so that you may be able to capture the most critical uh, member forces that you need in design. When service load, live load does not exceed three-fourths of the service dead load, then you may use the analysis, uh, the full dead and live load on all spans. And when the influence lines are used as basis for load patterns, okay, only three-fourths of the factored live loads may be used, provided you have to check that this should not be, the result of this should not be less than uh, the result of those which are coming from the factored moments, to see to it that your design will not be critical in case uh, the influence line patterns are not the ones that are prevalent, no, in the actual behavior of your structure. So that's it uh, for the conclusion of your ACI direct design method and equivalent frame method. I hope you have so far distinguished the difference between the two, and appreciate the advantages of one over the other. Thank you very much for listening. I'll see you on my next lectures concerning maybe slenderness uh, concepts, which is also very important in building analysis. Thank you very much and have a good day.